So we're going to start with number 4. So the problem says that for 4a, if n is odd, then 5 2n is equivalent to 5n. So let's just write down what we know. So n is odd and 2 is even. So one thing I can immediately tell from this is that the GCD of 2 and n must be 1 because n is odd and therefore it can't be divisible by 2. So what this tells me is that since the GCD of 2 and n is 1, I can use the fact that the phi function is multiplicative in this case. So I can say that phi of 2n is equivalent to phi of 2 times phi of n. So now let's reduce this a bit. Well, phi of 2 is just, let's use our formula. So side note, phi of n equal to n times the product of all the primes that divide into n times 1 minus 1 over p. So in this case, what's phi of 2? Phi of 2 is just 2 times the product of all the primes that divide into 2. Well, in this case, that's just 1. Well, that's just 1 prime because the only prime that divides into 2 is the number 2. So that's 2 times 1 minus 1/2, which equals 1. So that means phi of 2 equals 1. So that means phi of 2n equals phi of 2 times phi of n, which equals 1 times phi of n. So this is kind of the shorthand way to write it. You could write that phi of n equals the prime factorization p2 a2 dot 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 p to the n a to the n, and then 5 2n is equivalent to the same thing. So it's 2 times p1 a1 p to the n a to the n. But the idea is that phi of 2, that's the trick, that you eventually end up with 2n, but since 2n, 2 divides into that. So that's the trick. So now we have a 1/2 here, which will cancel out for the 2, giving us just n. So that relates back to the problem that the 2 is basically going to go away. So then we just end up with getting 5n. So if we look at the next part, it's a little bit similar. So number 2 asks that phi of 2n equals 2 times phi to the n, phi of n, given that n is even. So this is a bit similar to part A. So let's review what we did in part A. In part A, we did phi of 2n equals phi of n times phi of 2. However, that was under the condition that GCD of n and 2 equals 1. But since the fact that n is even, that means 2 divides into n. Therefore, this statement isn't true. And because of that, we can't say this expression. So we have to think of an alternate strategy to approach this problem. So let's try writing out what explicitly what phi of 2n represents. So in terms of prime factorization, since n is even, we know one of the terms is going to be 2, right? So 8, that's 2 cubed, or 34, 2 times 17. It's always going to have some number amount of 2's in them. So we can say that mysterious amount as k1. And then we can rewrite all the primes out. So k2 dot 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 p to the k, or p to the n, kn. So if we have 2 to the n, that additional 2 will increase this 2. So then what I mean by that is instead of having k1 as our exponent, we're gonna have k1 plus 1. And then everything else remains the same. So let's see how that affects our phi function. So phi of 2n, well, it's this quantity right here. So 2 to the k1 plus 1, p2, k2, dot dot dot, p to the n, kn, and then all the products p that divide into this nonsense. I'm just going to write a squiggly here for saving time. And then 1 minus 1 over p. So let's rewrite this product stuff. So we have 2 to the k1 plus 1. So instead of writing that, I'm going to take out a 2. So I'm going to 2 to the k1, p2, k2, p to the n, k to the n. I'm still having the products here, right? So p dividing dividing to that nonsense squiggle here, 1 minus 1 over p. So notice that since I'm dividing 2n and dividing n, what does the number of primes change into there? So what I mean by that is if I have p dividing into n, I know 2 is a possible prime number, p2 and pn. These are the finite possible primes that divide into n. So p to the 2n, I'm not introducing any new primes. The only thing I increase is there's an extra factor of 2 that goes into the quantity 2n. So as a result, I still have the same distinct primes that originally divided into n. So notice that since I take out 2 here, if you notice, this is just n, and then this is just the number. This represents the product of primes that divide into n as well. So as a result, I can represent that as 2 times phi of n. And then I'm done. Okay, so number 3 asks something similar. It asks prove phi of 3n is equivalent to 3 times phi of n. And this is only if 3 divides into n. So again, since the GCD of 3 and n is not 1, I can't say it's multiplicative. So again, we got to think of something alternate. So let's write it out to see if we get an idea. So n prime factorized, let's say p1 to the k, and since divisible by 3, I know 3 has to be a prime to some amount, 3. So then p2, k, p3, dot, 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 p to the n, k to the n. So therefore, 3n is the same thing, just except one more power of 3. 3k2 plus 1, p3k3. So with this plus 1, I kind of already have a hint of where I'm going to go, that I need to manipulate 3n and factor out that 3. So let's see what I can do. So with phi of 3n, I can say that it's phi of all the prime factorizations, right? p1 to the k1, 3k2 plus 1, dot, 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 p to the n, k to the n. Well, let's do some grouping then. With this, I can group it together such that it's phi times 3 to the k2 plus 1 times phi to the p1, k1, dot, 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 p to the n, k to the n. So how I set this up was I used the multiplicative thing. So what I did was I grouped all the 3's together and then all the things that weren't 3. So basically what I did was I did phi of m times phi of n. Now this trick is legal because the GCD of m and n in this case is 1. Why? Because I grouped everything that was a 3 here and everything not a 3 here. That way this is not divisible by 3. So therefore the GCD has to be 1. So with this in mind, let's do some reducing. With this, I can rewrite this as 3 to the k2 plus 1 times 1 minus 1/3, because that's the 1 minus 1 over p nonsense, multiplied by the phi of all my other primes, pn to the kn. So here's where that trick came in. This is that plus 1, right? So let me rewrite this. 3 times 3 to the k2, 1 minus 1/3, times phi of all my other nonsense. So this isn't written as formally, but basically it's like that. Look at n, right? That's all the prime factors, but notice it's 3 to the k2. So writing phi to the n out, it's, well, think about it. It's phi times all these factors, and sorry, let's rewrite that in. So let's backtrack. We're at this step. Basically, it's this encircled represents phi to the n. And that's because we already have the 3 to the k2 factored out. So if I reduce this phi product, it's 3 to the k2, 3 there, multiplied by all my primes. And I still have that 1 minus 1/3 from before, multiplied by all my new primes, dot, dot, dot. And now this quantity is n. So now I just have 3 to the n. Okay, let's focus on D. Part D asks the following, that phi of 3n is equal to 2 times 5n, if and only if 3 does not divide n. So the so this one's a bit easier. So immediately, 3 does not divide n, right? So I already know the GCD of 3 of n is equal to 1. So my first mentality should be like, rewrite this with a multiplicative theory. That's 5 times 5n. With that in mind, phi of 3 is just what? It's just 3 times 1 minus 1/3, which equals 2 times 5n. And that's literally it. The longer way would be demonstrating what 5n is and representing all the primes out. But because we know the GCD of 3n is 1, we can just do this shorter way and separate it out. The last one is phi of n is equal to n over 2 if and only if n equals 2 to the k. So the hint they gave us is, right, n equals 2 to the k times n, where n is some odd number. So they're asking phi of 2 to the 2k times n equals what? Yeah. Sorry, my throat's a little raspy. Oh! So the idea is n is odd. So because n is odd, it's never divisible by 2. So I can say GCD of 2 to the k, comma n equals 1. With that, I can say that phi of 2 to the k times n equal to 5 times 2 to the k times 5n. And then from there, I can say that what's 5 times 2 to the k and what's 5 times n? Because that's pretty much what they're asking. So with that, I can say that that's 2 to the k. What's the only prime that divides into 2? That's 1 minus 1 over 2. 5n, that's still a bit mysterious to me. So I can just write n times all the products that divide into n, and of course 1 minus 1 over p. But I know this has to equal n divided by 2. So they want me to prove that n equals 1. So I can't do that at this point. So let's reduce the math a little bit. So this is going to be 2k over 2 times n times pi p divided by n 1 minus 1 over p equals n over 2. So since n is 2k over 2, that's 2k here instead of that n. So notice that these parallel. So the only way that this entity can ever equal 1 is if n equals 1. And that's because if n equals 1, the only prime that divides into n is nothing. So I'll just have nothing here, and this reduces to n, which is just 1. So you had a question about the summation, so let me just write it out. So the summation of n to the k, q to the n, 1 minus q to the n. So let's just start from there. We need to recall the geometric series. So recall that if I have a series like 1 plus 1/2 plus 1/4 plus 1/16 dot 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 dot, and I want to sum that all up, I can represent all this as a times 1 over 1 minus r to the n, where r is somewhere between 0 and 1. Well, let's just represent this a little algebraically. I can say 1 plus x squared dot 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 is equivalent to 1 over 1 minus x squared. So given this fact, let's apply that here. So the summation of n to the k, q to the n over 1 minus q to the n. Well, notice that this is like this. So instead of writing 1 minus q to the n, let's just write it in terms of the whole sum. So that's the summation of n to the k, q to the n, times 1, so 1 plus q, 1 plus q squared, 1 plus q cubed, all the way to q to the n. So I think your question was, how did you get from the line afterwards? And the line afterward is the summation of n to the k times q to the n times the summation of q to the an, where a ran from 0 to n. So I like that quote he said in class. You have to look for information where you think there wouldn't be one. So notice that things are being changed here. What? It's the exponent of q. Q to the first, q to the second, q to the 3, all the way q to the n. But what about 1? That's in disguise q to the 0, right? So notice there's a variable changing. 0, 1, 2, 3, 4, 5, 6, etc. I can represent that as an exponent, a variable that's changing, some type of parameter. So that's where we get the term q quotation a, right? It's just some number a to the n. So think about what happens when you plug in something. If I plug in 0 for a, then I have 1. If I plug in 1 for a, I get q to the first power. If I plug in 2 for a, I get q squared, all the way to q to the n. And then from there, I can do some groupings. I can say, well, I think you understood the rest. But anyways, n equals 1, a equals 0, and then we can group this together. N to the k times qn times a plus 1. And then from there, you can represent everything in terms of m, and then finish the proof. So the key idea here was just manipulating the geometric series to get this part.